Math 2414, Taylor and Maclaurin series, video 8, Maclaurin series for cosine of x. Now, if you just got finished watching the previous video, we built the Maclaurin series for sine of x, found its interval of convergence, which was all real numbers, and even verified that the Maclaurin series did converge to sine of x by using Taylor's formula for the remainder, the difference between the function sine of x and a Taylor polynomial where we take the series and cut it off somewhere. And we showed that the remainder approached 0 as k went to infinity by using Taylor's, Taylor's theorem shows that when that remainder approaches 0, then the series does converge to the function. And we use Taylor's formula to represent the remainder in closed form as basically as the next term in the series, but we put in some value z into the derivative, some z that's between the center and the x. But regardless, we're going to do the Maclaurin series for cosine. And you might be thinking, oh great, we have to do all that again. Well, no, on two levels. Number one, we're not actually going to show that this series converges to cosine of x by showing that the remainder converges to 0 as k goes to infinity. We're just going to find the series for cosine of x. And the other level of no is we're not going to do it by actually using the definition of a Maclaurin series, which is a Taylor series centered at 0. We're going to use the previous results to get this result. Now, what do I mean by that? Well, in the previous video, we came up with the Maclaurin series for sine of x. It was the sum from n equals 0 to infinity of the alternator, -1 to the n, over an odd number factorial, 2n plus 1 factorial, which will actually start with 1 factorial when you put 0 in for the n. And then it was x to that power, x to the 2n plus 1. And when we expanded it, it was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. We'll take it out one more term, minus x to the 7th over 7 factorial. Or we could put the powers of x to the right of the fraction and write something like minus 1 over 3 factorial x cubed, if you prefer your coefficients in front of your x's instead of underneath them. And of course, this went on forever. And the interval of convergence, this converges for all x an element of -infinity to infinity. And again, if you're watching this video and haven't watched previous ones, you may be wondering what that symbol is. I introduced it a couple of videos ago, but just to give it its due diligence here without too much ballyhoo, this symbol looks like an upside down A, or the head of a bull or a cow, is a symbol for the phrase for all or for every. It's called a universal quantifier. Basically says for every x in the interval, this series converges. So if we're going to find the series for cosine of x without reinventing the wheel, how are we going to do that? By taking advantage of what we know about the relationship between sine and cosine, at least from a calculus perspective. And what is that relation? Well, if we take the derivative with respect to x, then the derivative of sine x is cosine x. And in previous videos about power series, we had mentioned that if we have a series that converges on an interval, then the derivative and the antiderivative of that series will also converge in the same interval, except possibly at the endpoints, which we could check separately. So when we take the derivative of the series, it's not going to change the interval of convergence, and there are no endpoints to check because this interval is infinite on both sides. So all we have to do is take the derivative of our series for sine, and we got our series for cosine. Let's start on the right side and just do regular old differentiation, the derivative of each of these terms. Well, the derivative of the first term is easy. The derivative of x is just 1. But how do we take the derivative of x cubed over 3 factorial? Well, just take the derivative of x cubed and leave it over 3 factorial. And we could leave it like that, but think about the 3 on top of the 3 factorial. Because isn't 3 factorial just 3 times 2 times 1? And as a consequence, we can cancel the 3's. and what's left over is 2 times 1, better known as 2 factorial. I think that'd be a cleaner way to write this. So instead of writing it as minus 3x squared over 3 factorial, let's just write it as minus x squared over 2 factorial. And if we do the same thing to the next term, the x to the 5th over 5 factorial, then we're going to get 5x to the 4th over 5 factorial. But the exact same thing as before. The 5 on top will cancel with the first part of the factorial. It'll cancel the 5, but it would leave the 4, 3, 2, 1 once we cancel the 5s. So canceling a 5 with a 5 factorial would leave a 4 factorial. We better cancel that 5 on the top. And we start seeing this nifty little pattern that is kind of like we had before, but now instead of odd powers and factorials, it's even powers and factorials. So what's the derivative of x to the 7th over 7 factorial going to be? You think about it. You would bring down the 7 in front of the x to the 6th, but that 7 would cancel with the first factor in 7 factorial, leaving 6 factorial. So we get kind of the same phenomenon that we have with sine of x, but now instead of the odd powers oscillating over their factorials, it's the even powers oscillating, or excuse me, alternating in signs over their factorials. So how would we write this in sigma notation? Well, let's start by just taking the derivative of the term inside of the sum for sine of x. Let's just start by taking that derivative right there. Well, the negative 1 to the n would sit there because that doesn't involve an x, so we're differentiating with respect to x. The 2n plus 1 factorial has no x's. It's a constant relative to x. The only thing that we would differentiate is the x to the 2n plus 1 by bringing down its power and lowering the power by 1. So now the power is 2n. But we get the exact same canceling phenomenon that we had over here. The number that we just brought down by taking the derivative, in this case 2n plus 1, is the first factor in the factorial, and so the 2n's plus 1 would cancel. And what would that leave? Well, if the 2n plus 1 canceled in the denominator, then the factorial would start with 2n. And if we cancel that 2n plus 1 on the top, then we would have x to the 2n power. And frankly, I think it would look a little bit better to the right of it. I personally prefer my coefficients in front of x's instead of under them, but I'm good with either. And because when you take the derivative of a power series, it doesn't change the interval of convergence, this series also converges for all x, for all real numbers between negative infinity and infinity. I'm not going to go through the Taylor's formula and Taylor's theorem to show that this series, the one that we just found, which I'm about to highlight, to show that this series does indeed converge to cosine of x. We could do the ratio test, but all that shows is that the series converges. It doesn't show that it converges to that. That's what Taylor's formula and Taylor's theorem gets us. So yeah, the series for cosine is just like the series for sine, except it's all the even powers and factorials instead of the odd powers and factorials. And if you really know your sine and cosine, then this shouldn't surprise you, because cosine is an even function, meaning that putting in x and negative x gives the same results, which will happen here because all the negatives would cancel. And sine is an odd function, meaning putting in an x and a negative x give opposite results. Putting in a negative for all the x's there would change every term sign and give you the opposite results. Both of these series need to be memorized. No kidding around. End of story. Know them. Did I mention you need to memorize these? Yeah, I did.